Good morning, class. In this video, I'm going to solve for the quantum mechanical particle on a ring. So the first thing that we need to do is write out the kinetic energy. So the kinetic energy is equal to p squared over 2m. There is no potential in this problem, or at least the potential is 0. The momentum is in 2 dimensions. So the momentum vector has an x component plus a y component. We can take the dot product of this vector with itself, and when we do, we get px squared plus py squared. And now our kinetic energy is equal to 1 over 2m px squared plus py squared. And this, since the potential is equal to 0, this is also what our Hamiltonian is equal to, just the kinetic energy. Now what we can do is we can take our momentums and turn them into operators. And then we can put them into the Hamiltonian. Now when we square both of these, the negative sign is squared, so it's positive. The I is squared, so you get a negative. And h bar is squared. So we're actually going to have a negative h bar on each one of those momentum. So we have the second derivative respect to x, second derivative respect to y. Now also remember that the Hamiltonian acting on the ket gives us the energy. So therefore, this expression right here can be written as 2m e negative h bar squared all right. And of course we're acting on a wave function here. All right, so the next thing that we need to do, since our particle, at least for this problem, the particle is moving around in a circle, so a coordinate system that seems more suited for this problem is going to be cylindrical coordinates. And we're in Cartesian right here, so we're going to convert our problem into cylindrical coordinates. So we have that x is equal to rho cosine phi, and y is equal to rho, that's a rho, sine of phi. So we're going to need the derivatives of our our eigenstates. So this is going to be our eigenstates. And here the derivatives of the eigenstate, or the wave function, is with respect to x and y. We actually want it with respect to rho and phi. So let's use the chain rule. Let's see if we can figure out what this is. So we can use it a second time. So we can see that this term is going to equal 0, and so is this term. So now, with respect to phi, all right. So these are the only two left here. Now what we're going to have to do is we're going to have to figure out what the derivatives of these are. So let's just write those down. Now, with respect to phi, all right, so we can relate the derivatives with respect to phi to the derivative with respect to rho. For example, cosine phi is actually equal to the rho derivative of x. And here we have a cosine, and here we have a cosine. Same thing with the sine as well. So now we can say x of phi is equal to negative rho y of rho. X of phi is equal to negative rho x rho. Y, at least the phi derivative of y, is equal to rho times the rho derivative of x. And lastly, we have the second derivative of y with respect to phi. All right. Okay, so let's work with this one. Maybe we can label these. I started to label them, but let's label them. Whoops. A, B, C, and D. So let's go with B first. So B is equal to, and that is actually a rho, not a phi. And we can see that the rho derivative of x is cosine, it's sitting right there, and it's squared. And the rho derivative of y is equal to sine, and that's squared. So this actually equals psi xx cosine phi squared plus psi y sine of phi squared. All right. So now let's go to D. So this one's going to need a little bit of work. These are phis. Now we can start making substitutions right away. So this term right here is sitting right here. Yeah? So we can just make that substitution right away. So we're going to get a negative rho y rho squared plus psi of x. And this term right here is sitting right here. So we get a negative rho x rho. And then we have plus psi, second derivative of psi with respect to y. And then this term right here, sitting right here. And that is a rho. And it's squared. And then the last term, sitting right here. That is a rho. All right, so the next thing that we're going to do is we're going to divide. So we're going to be working on this one for a little bit here. We're going to divide by rho squared. And let me just make that a little bit nicer. So on this one, get psi xx, y of rho squared. This one, we're going to have, this is actually going to be negative. You know, I tell you what, I'm going to take this one and put them next to each other. All right, and now this one, which, remember, I'm dividing through by rho squared, so I'm going to have a 1 over rho psi of x, x rho. And then now this one, negative 1 over rho psi of y, y rho. Okay. So now, let's continue. Now, y, the derivative of y with respect to rho is sine, and it comes in squared. So we have this times sine squared plus second y derivative of psi. And we have the rho derivative of x, which is cosine. So this is cosine phi squared. And now, if you look, a, right here, that actually appears right here, the last two terms. So I'm going to have this, and I'll just write this out so you can see what it is. I'm going to factor out a negative 1 over rho. So this is actually equal to a. So maybe I just write it that way. So it's psi of rho. So let's just say A psi of rho. Okay? So now we have 1 over rho squared, second derivative of psi with respect to phi. And I'm going to bring this whole last factor, I'm going to bring that over, actually I need more space here. I'm going to bring that over to the left. So let's write this over here. When I bring it over to the left, it becomes positive. We have a psi of rho. Okay. And we have second derivative of psi with respect to x, sine squared, phi, and then the cosine term. All right. So we have this equation, and we have this equation. And actually, I'm going to maybe change this just a little bit. There we go. So what we're going to do is we're going to take 1 and 2, and we're just going to add them. But you can see when I add this first term right here with the cosine squared, this is the same one here, but it's sine squared. So when I add these two, I can factor out the second derivative with respect to x, and then I'll have the second derivative with respect to x times cosine squared plus sine squared, which is 1. So on the left-hand side, when I add all this together, we're going to get second derivative with respect to, that should be rho. We already have this derivative with respect to rho. So remember, we're adding equations 1 and 2. So I'm adding the left-hand sides now. And now the right-hand side. Okay, and this is what we have in our expression right there. So we can replace that with this right here. But there is one more step, but I'll write it all out on the next page here. So that gives us, again, going back over to here, right there. So that's going to give us this. Okay, now in our problem, rho is equal to capital R, which is a constant. That's the radius of the ring. So that means that these derivatives with respect to rho are going to equal to 0. So our equation reduces to this. Okay, so now we want to solve this. So, and I'm actually going to call this capital R squared. Okay, so remember we have this particle moving around a ring. And this particle has a moment of inertia. And that moment of inertia is given by mr squared. Okay? So that means that this mr squared we can write as I, the moment of inertia of the particle. Okay, now we're going to let m squared equal to 2I e, the energy, h bar squared. And we're going to write this as such. Yeah, we're just going to make that substitution. So we can try the solution. And this should be obvious if I take the second derivative of this with respect to phi. Each time I take a derivative with respect to phi, I pull down an im. So if I pull down two ims, I have I squared, which is negative, and I have m, which is squared, and then the psi back. And that's exactly what we get over here. So this is our solution. Of course, we need to normalize it. Okay. So let us go ahead and normalize this first. Well, taking the modulus squared of this just gives us n squared, 0 to 2 pi, and that should be equal to 1. So that means that 2 pi n squared, right, this right here, is equal to 1. And that means that n is equal to 1 over the square root of 2 pi. So this is our properly normalized wave function. Okay, so there's a couple more things that we need. We need to figure out what the energies are, and we can do that. So what's going to happen as this quantum particle is moving around the ring, it's going to be setting up a standing wave. And as you go around the ring, the wave function needs to be single valued. So the wave function must be single valued. And what that means mathematically is that as you go around the ring, 2 pi and come back to where you started, because as you go around the ring once, you come back to where you started, and that is 2 pi around the ring. So that must mean, for the angle that is, right? And so that must mean that the wave function at phi must be equal to the wave function at phi plus 2 pi, because you come back to where you started, and the wave function must be the same. So let's go ahead and stick our wave function in. And we're going to forget about the factor out front because it's going to appear on both the left and right hand side. So we have, for the left, Im phi, and on the right, Im phi plus 2 pi. So this gives us 1 e to the I m 2 pi. Now we can use Euler's identity. Cosine of m 2 pi plus I sine of m 2 pi, and that should be equal to 1. Now this is real on the right hand side, so that must mean that this is equal to 1 and this is equal to 0. So let's see what those conditions give us. So sine of m 2 pi equal to 0? Well, sine is 0 when its argument is 0 or pi. So that must mean that m is equal to 0, because when m is equal to 0, the argument is 0. Or it can equal to plus or minus 1. So plus or minus 1 would be plus or minus 2 pi. Yeah. So this is also equal to 0. And this keeps on going for all integers like this. Cosine of m 2 pi, well, this is supposed to be equal to 1. And it will equal to 1 when the argument is equal to 0, 2 pi, right, 4 pi. And that happens when m is equal to 0, plus or minus 1, plus or minus, getting a little carried away there, plus or minus 2, and so on. So now we have, for the solution of a particle on a ring, we have as its wave function and maybe we'll put a little m there for its quantum number, and we'll write down what the quantum numbers are. So on. And we can come back up here, and you can see here's the energy right here. So we just need to solve for the energy, and we're going to put a little subscript on that, since m is quantized. So we have m squared h squared over 2I. So these are the energy eigenvalues of the problem. And that's it.